Deployment of AI-driven military simulations by 2024, a comprehensive overview. Introduction. The advancement of technology in military operations is pivotal for enhancing the capabilities and effectiveness of the Department of Defense (DoD). The deployment of AI-driven military simulations by 2024 represents a transformative initiative to modernize military training, enhance strategic assessments, and streamline acquisition processes. This report outlines the critical phases involved in this deployment, the associated investment of $3.2 million, and the implications for future military operations. 1. Current state of digital transformation (DT). The DoD is currently navigating a comprehensive digital transformation (DT), transitioning from traditional document-based systems to model-based approaches. This shift is essential for integrating automated digital testing throughout the acquisition lifecycle, allowing for rapid responses to evolving military needs. The current landscape reflects the necessity for modernization in military operations to keep pace with technological advancements and emerging threats. 2. Model-based systems engineering (MBSE). Model-based systems engineering (MBSE) is a cornerstone of this digital transformation. The adoption of MBSE enables the creation of interconnected digital models that improve communication and efficiency across departments. A notable example is the U.S. Navy's investment in MBSE practices, which resulted in significant cost savings and demonstrated the potential return on investment (ROI). MBSE facilitates a more agile and responsive framework for developing military systems, ensuring that all stakeholders have access to accurate and up-to-date information. 3. Test and evaluation (TNE) methodology. A fundamental aspect of the transformation is the integration of test and evaluation (TNE) early in the development process. The concept of test and evaluation as a continuum (TEaaC) emphasizes continuous assessment and validation of models and systems throughout their lifecycle. This approach mitigates the risks associated with late-stage errors that can be costly in terms of time and resources. By shifting TNE to earlier phases, the DoD can identify and address potential issues before they escalate, resulting in more reliable military systems. 4. Validation framework. The proposed validation framework is crucial for ensuring that system models meet intended requirements. It includes specific use cases and methodologies such as validation test cases and model requirements to assess the credibility and reliability of simulations used in military operations. Developed by researchers at Wright-Patterson Air Force Base, this framework ensures that all models are rigorously tested and validated before deployment, enhancing confidence in their effectiveness. 5. Rapid Acquisition Process (RAP). The Rapid Acquisition Process (RAP) is designed to expedite the development and deployment of military systems. By leveraging digital TNE and capabilities-based testing, the RAP ensures that systems are validated and accepted quickly. This agility is vital for maintaining military readiness and adaptability in response to emerging threats. The RAP, coupled with TEaaC methodologies, enables the DoD to respond swiftly to the dynamic landscape of modern warfare. Timeline of events. Ongoing initiatives. The transition to MBSE and digital testing has been underway, with various programs already implementing these practices. 2024 target. The DoD aims to fully deploy AI-driven simulations and the associated validation frameworks by 2024. Enhancing decision-making capabilities and operational readiness. Investment. The $3.2 million investment is specifically allocated for developing real-time strategic assessment tools that will support this transition. Key points. The integration of digital testing in MBSE is crucial for the modernization of military acquisition. Early validation and continuous testing are emphasized to reduce costs and enhance system reliability. The RAP and TEaaC methodologies are designed to streamline the acquisition process and improve military effectiveness. Differences in perspectives. While various sources emphasize the importance of digital transformation in MBSE, there are differences in focus. Some highlight the rapid acquisition methodologies, while others delve deeper into validation processes and testing integration. The technical discussions surrounding automation and digital threads offer a more nuanced perspective on the implementation of these methodologies. Conclusion: the deployment of AI-driven military simulations by 2024 is a significant step forward in modernizing the DoD's approach to military readiness. Through enhanced modeling, testing, and validation processes, the initiative aims to create more efficient and effective military operations. The integration of digital transformation MBSE and advanced testing methodologies will empower the DoD to respond to emerging threats with agility and precision, ultimately leading to a more capable and adaptable military force. The deployment of AI-driven military simulations by 2024 involves a multifaceted approach that includes some counterintuitive elements regarding the integration of traditional and modern methodologies within the Department of Defense (DoD). Here are several key insights that may initially seem surprising. 1. Shift from traditional testing to continuous assessment. Traditionally, testing and evaluation (TEaaC) in military acquisition have occurred at the end of the development cycle. This method often leads to significant costs when errors are identified late in the process. The counterintuitive aspect here is that by integrating TEaaC as a continuous process throughout the development lifecycle rather than as a final step, the DoD aims to reduce the overall costs of acquisition. This shift emphasizes early detection of issues, which contradicts the conventional belief that testing should be reserved for later stages when systems are more fully developed. 2. Model-based systems engineering MBSE as a cost-saving tool. While MBSE is often perceived as a complex and costly approach to systems engineering, studies have shown that its implementation can lead to considerable cost savings. For example, the U.S. Navy reportedly saved $10 million through the investment in MBSE practices. This challenges the common notion that new methodologies are inherently more expensive and difficult to implement, suggesting instead that they can provide significant long-term financial benefits. 3. Integration of digital tools with legacy systems. The initiative promotes replacing document-based systems with digital models, which initially seems disruptive. However, the integration of MBSE and automated digital testing with existing born analog systems, legacy systems, is expected to enhance performance rather than complicate it. This counterintuitive perspective emphasizes the adaptability of new technologies to improve the efficiency of older systems, which often face challenges in modernization. For Rapid Acquisition Process (RAP) and Agile methodologies, the RAP is designed to accelerate the development and deployment of military systems. While rapid methodologies may seem to favor hasty decisions, the incorporation of structured digital validation processes actually promotes thorough evaluation and assurance of system capabilities, which is contrary to the perception that speed compromises quality. 5. Emphasis on validation frameworks over traditional verification. The proposed validation framework prioritizes the credibility and reliability of models used in military simulations, which may seem to detract from traditional verification methods. However, this emphasis on validation, ensuring that models accurately represent real-world conditions, actually enhances the overall trust in the simulation outcomes, challenging the notion that verification alone is sufficient for rigorous testing. 6. Real-time strategic assessment tools investment. The $3.2 million investment in real-time strategic assessment tools may appear modest compared to the vast budgets typically associated with military projects. However, the strategic focus on improving decision-making capabilities through these tools indicates a shift in perspective, where the value of timely and accurate information is prioritized over large-scale hardware investments. 7. Interconnectivity of models and digital threads. The reliance on interconnected models and digital threads to create a comprehensive view of system requirements and performance might initially seem overly complex. Yet this approach enhances communication and understanding among stakeholders, presenting a counterintuitive benefit where complexity leads to improved clarity and collaboration rather than confusion. 8. Educational integration of digital practices. the application of these advanced methodologies in educational settings such as the Air Force Institute of Technology's curriculum suggests that the next generation of military leaders will be trained in these innovative practices. This integration may seem premature, but it prepares future personnel to adopt and implement these technologies, effectively challenging the assumption that significant changes should be reserved for more mature stages of career development. 9. Automation in testing. The notion that automation may replace human oversight in testing could evoke concerns about reliability and accountability. However, the reality is that automated testing can enhance accuracy and efficiency, allowing human testers to focus on higher-level analysis and decision-making. This counterintuitive advantage reduces the burden on human resources while increasing overall system reliability. In conclusion, the deployment of AI-driven military simulations by 2024 embodies several counterintuitive aspects that disrupt traditional military acquisition and operational practices. By embracing continuous assessment, integrating modern methodologies with legacy systems, and prioritizing validation and real-time tools, the DoD is not only addressing current challenges but also setting a foundation for future advancements in military readiness and effectiveness. The report on the deployment of AI-driven military simulations by 2024 outlines critical advancements in the Department of Defense's DoD approach to military readiness and operational efficiency. While many aspects of the report are significant, several important content points may be easily overlooked, which are crucial for understanding the broader implications of this initiative. 1. Digital transformation and model-based approaches. The transition from traditional document-based systems to model-based approaches is a foundational change that underpins the entire initiative. This shift is not merely a technical upgrade, it represents a cultural change within the DoD. The adoption of model-based systems engineering (MBSE) is pivotal as it allows for interconnected digital models that streamline communication and enhance efficiency. Significance: this change will fundamentally alter how military systems are designed, tested, and deployed. The emphasis on digital transformation can lead to significant cost savings and increased agility in responding to emerging threats. For example, the reported savings of $10 million from the U.S. Navy's investment in MBSE practices illustrate the potential for a substantial return on investment (ROI). Many stakeholders may overlook the cultural implications of this transformation, which are just as critical as the technical advancements. 2. Test and evaluation as a continuum (TEaaC). The report introduces the concept of test and evaluation as a continuum (TEaaC), moving away from the traditional end-stage testing model. TEaaC emphasizes continuous assessment and validation throughout the lifecycle of military systems. Significance: this paradigm shift is essential for mitigating late-stage errors that can be costly and time-consuming to rectify. Continuous testing allows for immediate feedback and iterations, reducing the likelihood of deploying systems with critical flaws. However, the profound implications of early and continuous evaluation, such as the potential to innovate more rapidly and efficiently, may not be fully appreciated by all audiences. 3. Validation framework for system models. The proposed validation framework is crucial for ensuring that system models meet intended requirements. This includes specific methodologies for establishing credibility and reliability in military operations. Significance: the validation of system models is a complex and often underappreciated aspect of military simulations. The integration of validation techniques from the outset is necessary to build trust in the models used for decision-making in critical military contexts. Many people may overlook the importance of rigorous validation processes, assuming that accurate simulations are inherently guaranteed, which is not the case. 4. Rapid Acquisition Process (RAP). The RAP is designed to expedite the development and deployment of military systems, relying heavily on digital testing and validation to ensure rapid acceptance. Significance: the RAP's emphasis on speed is critical in an era where military threats evolve rapidly. The ability to quickly adapt and field new technologies can mean the difference between success and failure in military operations. The nuanced understanding of how RAP interacts with digital T&E might be overshadowed by the general focus on technological advancements. Yet it is foundational to the DoD's strategic agility. 5. Investment allocation and resource management. The $3.2 million investment for developing real-time strategic assessment tools is an important detail that may be overlooked. This investment is not just about money, it signifies a commitment to enhancing military readiness through improved tools and methodologies. Significance: the allocation of resources toward digital testing and assessment tools reflects a strategic prioritization of technological innovation. Understanding the significance of such investments can help stakeholders appreciate the long-term vision of the DoD regarding military readiness and operational effectiveness. It also highlights the importance of securing funding for transformative initiatives which can often be sidelined by budgetary constraints or competing priorities. 6. Implications for military culture and workforce dynamics. The report discusses the necessity for workforce adoption of new digital practices, emphasizing that successful transformation requires engagement at all levels of the DoD. Significance: the human aspect of this transition is crucial. Resistance to change can derail even the most advanced technological initiatives. The potential challenges and opportunities associated with workforce training culture shifts and the need for new skill sets are vital yet often understated components of successful implementation. Recognizing and addressing these factors can lead to smoother transitions and more effective outcomes. 7. Broader strategic context: adapting to emerging threats. The overarching goal of deploying AI-driven simulations is to enhance military effectiveness in the face of evolving adversaries and threats. Significance: while many may view the initiative as a technical enhancement, it is fundamentally about preparedness and adaptability in an increasingly complex global security landscape. The ability to use simulations to prepare for various scenarios can provide a strategic edge that is often underestimated. Understanding this context is essential for grasping the full impact of the deployment. Conclusion: the deployment of AI-driven military simulations by 2024 is a multifaceted initiative that extends beyond technological advancements to encompass significant cultural, strategic, and operational implications. The overlooked aspects discussed above are critical to understanding the initiative's potential impact on military readiness, efficiency, and effectiveness. As the DoD embarks on this transformative journey, recognizing the importance of these elements will be essential for stakeholders at all levels. 1. Digital transformation in the Department of Defense DoD. The DoD's transition from traditional document-based acquisition processes to model-based approaches is fundamental to modernizing military operations. This shift is necessary for integrating automated digital testing throughout the acquisition lifecycle, enabling rapid responses to changing military needs. The emphasis on digital transformation underscores the importance of leveraging technology to enhance efficiency in training and operational readiness. 2. Model-based systems engineering (MBSE). The adoption of MBSE is crucial for the success of digital transformation initiatives. By creating interconnected digital models, MBSE streamlines communication and contributes to significant cost savings. As evidenced by the U.S. Navy's return on investment in MBSE practices. Understanding the benefits of MBSE is key to recognizing its role in achieving more effective military acquisitions and operations. 3. Test and evaluation as a continuum TEaaC. The shift to integrating test and evaluation early in the development process as part of TEaaC is vital for reducing costs and enhancing system reliability. This approach, which emphasizes continuous assessment throughout the lifecycle, mitigates risks associated with late-stage errors. The transition from traditional testing methods to a continuum of evaluation reflects an agile methodology that is necessary for rapid acquisition processes. For validation framework and methodologies, The proposed validation framework developed by researchers at Wright-Patterson Air Force Base is essential for ensuring the credibility and reliability of military simulations. By incorporating specific use cases, model requirements, and validation test cases, this framework addresses the challenges of validating digital models. The integration of validation techniques within the overall acquisition process will ensure that systems meet intended operational requirements and enhance decision-making capabilities. 1. The Manhattan Project 1942–1945. The Manhattan Project was a research and development project during World War II that produced the first nuclear weapons. It involved a massive mobilization of scientific, military, and industrial resources across the United States. The project utilized advanced scientific modeling and engineering techniques to assess nuclear fission's potential and develop the atomic bomb. The rigorous testing and validation processes established during the project were critical for ensuring the weapon's effectiveness and safety. Paralleling the emphasis on model-based systems engineering, MBSE, and testing methodologies in the modern military technology landscape. 2. The Apollo Program 1961–1972. NASA's Apollo program aimed to land humans on the Moon and bring them safely back to Earth. It involved complex engineering challenges and extensive testing, including simulations and model-based approaches to ensure mission success. The program's rigorous test and evaluation methodologies, including the use of simulators for training astronauts and testing spacecraft systems, resonate with the current focus on AI-driven military simulations and real-time strategic assessments in the Department of Defense. Both initiatives underline the importance of early and continuous testing in achieving high-stakes operational goals. 3. The F-35 Joint Strike Fighter Program 2001–present. The F-35 program represents one of the most ambitious military aircraft development projects involving multiple branches of the U.S. military and international partners. The program has emphasized digital engineering, modeling, and simulation to streamline development and reduce costs. The integration of model-based systems engineering and continuous testing throughout the development cycle reflects the critical phases outlined in the deployment of AI-driven military simulations. The F-35 program's experiences with rapid acquisition processes and digital testing methodologies provide valuable lessons for contemporary military systems development initiatives. Future outlook: predictions for AI-driven military simulations by 2024. The deployment of AI-driven military simulations by 2024 is set to revolutionize the U.S. Department of Defense's DoD operational and strategic capabilities. This initiative, backed by a $3.2 million investment, will unfold in 5 critical phases, each contributing to improved military readiness and decision-making. Here are key predictions for the future of this endeavor. 1. Enhanced decision-making capabilities. By 2024, AI-driven simulations will significantly enhance the speed and accuracy of decision-making processes within the military. The integration of real-time data analytics will allow commanders to assess various operational scenarios and outcomes instantaneously. This predictive capability will enable more informed tactical decisions on the battlefield, reducing response times to emerging threats and facilitating mission success. 2. Widespread adoption of model-based systems engineering, MBSE. As the DoD continues to transition to MBSE, we can expect a broader adoption across various military branches. By 2024, MBSE methodologies will be standard practice, streamlining communication and collaboration among engineering teams. This will not only enhance efficiency but also promote cost savings, as evidenced by prior investments that yielded high returns on investment. Enhanced training programs will train personnel in MBSE principles, ensuring a skilled workforce adept at navigating complex systems. 3. Continuous testing and evaluation, TEaaC integration. The shift from traditional end-stage testing to a continuous TEaaC approach will reshape how military systems are developed and validated. By 2024, the test and evaluation as a Continuum TEaaC framework will be fully integrated into the acquisition lifecycle. This will lead to earlier identification of design flaws and operational deficiencies, thereby minimizing costly late-stage corrections. The seamless integration of digital testing tools will facilitate real-time adjustments to systems as they are being developed, resulting in more reliable and effective military assets. 4. Robust validation frameworks for AI models. The establishment of rigorous validation frameworks for AI-driven simulations will be a cornerstone of the deployment strategy. By 2024, the DoD will implement a comprehensive set of methodologies for validating AI models, ensuring that simulations accurately reflect real-world conditions. This will involve detailed use cases, model requirements, and validation test cases developed through collaborative efforts among various defense agencies. Such frameworks will bolster the credibility of AI-driven simulations, fostering greater trust in their operational use. 5. Accelerated Rapid Acquisition Processes (RAP). The introduction of RAP will expedite the development and deployment of military systems. By leveraging AI-driven simulations and enhanced digital testing, the DoD will streamline acquisition processes, allowing for quicker responses to evolving threats. This agility will be critical in maintaining military superiority amid rapidly changing global dynamics. Expect to see a marked reduction in the time from concept to deployment, with systems being fielded in a fraction of the time compared to traditional methods. 6. Increased collaboration with industry and academia. The successful deployment of AI-driven military simulations will foster increased collaboration between the DoD defense contractors and academic institutions. By 2024, we anticipate a surge in partnerships aimed at advancing simulation technologies and methodologies. These collaborations will lead to innovative solutions that leverage cutting-edge AI research and development, ensuring the U.S. military remains at the forefront of technological advancements in defense. 7. Adaptive learning capabilities. AI-driven simulations will evolve to incorporate adaptive learning mechanisms, allowing them to improve their accuracy and effectiveness over time. By 2024, we can expect simulations to analyze past operations and outcomes, learning from successes and failures to refine their predictive capabilities. This self-improving nature will enhance training programs, providing military personnel with increasingly realistic and challenging scenarios that prepare them for real-world engagements. 8. Ethical and strategic considerations. As AI-driven military simulations become more prevalent, ethical considerations regarding their use will gain prominence. By 2024, we predict the establishment of comprehensive guidelines and frameworks governing the ethical deployment of AI in military contexts. This will involve discussions on accountability, transparency, and the potential implications of relying on AI for critical military decisions. The DoD will likely prioritize ethical training for personnel involved in the development and management of these systems. Conclusion. The deployment of AI-driven military simulations by 2024 promises to transform the operational landscape of the U.S. military. With enhanced decision-making capabilities, robust validation frameworks, and accelerated acquisition processes, the DoD will be better equipped to address emerging threats and maintain strategic superiority. As these technologies advance, continuous evaluation and adaptation will be crucial to ensure that the military leverages AI responsibly and effectively, paving the way for a more agile and responsive defense force.